This example ties together several concepts that we may not directly relate to each other in the beginning, which is why I think it's a good one to go over. You're given some kind of potential that is good for all locations. It's in units of volts, and it's a function of x and z. And you're told that there's a conductor defined by z equals 0, so it's at z equals 0 and the region of x between 0 and 2, and y between -3 and 0. So you're told that in your free space on the xy plane, you have this region that is a conductor, and actually this drawing isn't completely accurate because the y is only in the negative half. So let me see if I can draw that more correctly. So x goes from 0 to 2 and y goes from 0 to -3. So you have this conductor that's laying here in the xy plane. This is x, y, and z. Now that's all well and good. The slight curveball is now you are asked, what is the charge on the conductor? So at first glance you might feel like, well, we don't necessarily have the information to do that. But with the knowledge that we learned from this chapter, we know that from the potential we can find the electric field. Right? If you know the altitude, if you have a map that tells you the altitude at different locations, or the elevation at different locations, you can take the gradient, and then that gives you the arrow map, right? So you can get the electric field by taking the gradient. And from this chapter, we know that when you come across a conductor, two things happen, right? In any kind of interface, the tangential components are continuous. E1 is equal to E2. In the case of a conductor, if E2 is a conductor, since the tangential field on a conductor is equal to 0, so you get that the field in the tangential component is going to be equal to 0. But also, the electric flux density is continuous in the normal component, and the difference is going to be so this is the actual thing that we learned, is that the difference between the normal component of the electric flux density is going to be equal to the surface charge density. And in this case, because again there's no electric field on the conductor, there's no the conductor, the charges can move around and cancel out any field you get, so the conductor is flat in elevation, right? If we were to use our 3D geography analogies. So the d2 is going to be equal to 0. So you also have this relationship that n dot d1 is going to be equal to rho s. And if you're given a rho s surface charge density, you can find the total charge on a conductor that's just defined as a surface. So our strategy is, first of all, we find E, and through that we can also find D. And then next up, we can use the fact that if we take the component that's normal to the interface, we can get rho s. And once we have rho s, since this conductor is just a surface, we can then find the total charge by simply integrating the surface charge density across the entire surface. So from here, we can kind of get a strategy for how to get to the total charge. Again, tying together some different concepts that we haven't related in the past. Well, let's start by finding the electric field from the potential. As I described before, if the potential were all the elevations, then the electric field would just be arrows that indicate how much downhillness a given location has across the entire map. So to do that, first of all, we find the gradient. So we take the slope in the different directions, but then we also add a negative sign, because if you take the gradient, that tells you the uphillness, and the electric field is defined as downhillness. So you add a negative sign so that you flip the direction. And we then have to take the gradient. So to take the gradient, we take the derivative with respect to x. Let's just pull out everything that's not x related. So that would be 100z. And then you have to take the derivative with respect to x of x over x squared plus 4. That gives you the component in the x direction. Now you might say, oh, now I have to do this derivative, but this is also a point to, this is also, if you think ahead, you also benefit from the fact that, hey, I'm only interested in z equals 0. That's the only location I'm interested in, right? So at some point, I'm going to do this derivative. I'm going to plug in z equals 0. And since whatever comes out of here is multiplied by z, if I'm only interested in z equals 0, that ends up being 0. So I don't have to worry about this component, which is good because I didn't really feel like taking that derivative. Though, of course, if I needed to, I totally could. Next up, take the derivative with respect to y, and that gives you the y direction. And what's the derivative of this with respect to y? 0, right? So thank goodness that part's easy. So far so good. And then the last part is to take the derivative with respect to z. So let's pull out everything that's not z, 100x over x squared plus 4. And then d by dz of z, which is just going to be equal to 1. That gives you the z component. And now don't forget that you also have this negative sign here, right? Don't forget that negative sign here. That often comes back to bite me, and it's my greatest hits in terms of common mistakes. So this ends up being 1, so you are left with negative of all of this in the z-hat direction. Your expression for the electric field is simply negative 100x over x squared plus 4 in the z-hat direction. So next up, let's move on to step 2, where now that we have the electric field, we also have the electric flux density, where we just have to multiply by epsilon naught. I guess I didn't say this is in a vacuum, but when in doubt, if it's never mentioned, just assume it's in a vacuum. Therefore, our d is going to be epsilon naught e, and we can find the surface charge density by taking the dot product of d with the normal vector for the surface. In this case, the normal vector for the surface is in the positive z direction. I think one way we can kind of define that is to just say that as z becomes positive, as it goes up, the potential goes up as z goes up. And so that's kind of one reason that by convention, you would probably define z as in the upwards direction. But in general, the direction of the positive current flow or the outward direction of a closed surface. When you can use either of those guidelines, those are what you use to determine the signage of the normal component. So in this case, the normal vector is simply z hat. So z hat dot, we'll just switch this to beginning, z hat, these two cancel out to just form 1, and you're just left with minus 100x all over x squared plus 4 as your surface charge density in coulombs per meter squared. Now you have everything you need. And remember, this formula is only good for the z equals 0 area, right, where we have the surface charge. And now we have a surface charge density. We revert back to chapter 1, chapter 2 knowledge, just where you say, I have a surface charge density. How do I find the total charge? So the total charge would just be equal to the surface charge integrated over the area. So now all that stands between us and victory is math, right? So, I forgot this epsilon naught here because we're looking at the electric flux density and not the electric field. Now we have minus 100 epsilon naught x over x plus x squared plus 4 dx dy, right? If we're integrating across this area where x goes from 0 to 2, y goes from minus 3 to 0. Let's separate this out. We'll have minus 100 epsilon naught and integral of minus 3 to 0 of dy, and integral of x goes from 0 to 2 of x over x squared plus 4 dx. This is simply going to be minus 3. This one is going to take a little bit more thinking. So going back to basic calculus skills, this is a u substitution scenario where you would set u is equal to x squared plus 4. Du is going to be equal to 2x dx. Therefore, dx is going to be equal to du over 2x. You plug those in, and you'll see that your x's cancel out, which is nice and happy. I'll just multiply this negative 3 out, so I get 300 epsilon naught. And then in this case, let's see, I have x 1 over u, and then I have du over 2x. These x's cancel out. And now, and let's just keep this as at x for the time being. But I'll just explicitly state that it's x so I don't forget when I say 0 to 2. And so now I have this 2 that I pull out, and u is just simply going to be ln of u, where u is going to be x squared plus 4. Let's plug that back in, where we evaluate it from 0 to 2. And that's going to give us 150 epsilon naught. And your pre-electromagnetics math skills really all get tested in this particular instance. But if you have natural log, you plug in 2, you have natural log of 16 minus the natural log of, if you plug in 0, you get 4. And remember, if you have the difference between two natural logs, you can combine this into natural log of 16 over 4. So you're left with natural log of 4. And finally, you arrive your answer of 150 epsilon naught natural log of 4 coulombs. And so, and the main thing I want to, again, emphasize the process, because I think that without this, the main point of this exercise is you're given a potential, you want to find the charge on a conductor. That should kind of trigger this kind of strategy in your mind, this kind of approach where you're given the potential or some other quantity that allows you to find the E field and electric flux density. And you can use that, you can use the boundary condition in the case of a conductor to find the surface charge density. And that could be the end result that you're looking for, or it could also allow you to find the total charge. But either way, you can go from potential to charge on a conductor by applying the boundary condition trick.